Hey there, this is Math 148 and we're looking at section 9.4, and this has a whole bunch of derivative formulas. And for those of you that thought that the section 9.3 and having to find the derivative using the limit definition, remember this thing, as h goes to 0, if you found all of that to be pretty tedious, then you will like these derivative formulas. So this section outlines five essential formulas. And the very first formula is my absolute favorite of the derivative formulas. It's the power rule. Power rule rules. Because this one is your friend. You guys might think, I'm taking Math 148 all by myself in my house, but you're not. You're taking it with the power rule because it is your friend and it's going to follow you through this entire class. So here's what the rule says. F of x equals, if the function looks like this, f of x equals x to the n, where n is some number, then the derivative, f prime of x is equal to n, you let the little exponent jump in front, times x, and then you subtract 1, n minus 1. So here's an example of some of these. If you had f of x is equal to x cubed, then the derivative, f prime of x, I like prime, it's kind of that's my favorite of the notations, is 3, the exponent hops in front, x to the subtract 1 makes that 2. Let's look at another case of the power rule. Suppose you had f of x is equal to x. What? That's not the power rule, but it is the power rule because if there's a 1 there, think of that, right? X is really x to the 1. Then the first derivative, x prime of x, is equal to, the 1 hops down in front, 1 times x, subtract 1 to the 0 is equal to 1. So if you have f of x or some function y just equals x, then the derivative is equal to 1. This is something that you can use with the power rule, who is your friend, or you'll just get used to it and memorize that as sort of a separate little rule. So that was rule number 1, was the power rule. Here's rule number 2. Rule number 2, your book calls it the constant rule. Basically, if the function is a constant, if f of x is equal to some constant c, then the derivative is equal to 0. So, as an example, if you had f of x is equal to 6, then the derivative, oops, I don't know where I got the y, the derivative of f of x equals 0. So the derivative of a constant is always equal to 0. Here's the third rule, is the sums. I'm not going to write out the formal definition because it's in your book and it's just a little bit wordy, but basically saying that the sum of the derivatives is the derivative of the sums. We can add derivatives. So let's say you have f of x equals x squared plus x cubed. So I think this is easier to show you with an example than with the formal definition. So the derivative, we can just take the derivative of this piece, which is 2x, right? Power rule, exponent jumps in front, subtract 1, plus the derivative of this piece. Power rule, 3x squared. Again, the exponent jumps in front, subtract 1. So I took this derivative by taking each one and then adding them together. So we can add derivatives, which is very handy, and if we can add them, we can also subtract them. You like how I went from, yep, there we go. Maybe there's only 4 rules. Oh, I remember, I'm missing one, hold on. Difference, I'll get to it. The difference rule is f of x, you can subtract them. Suppose f of x is equal to x squared minus x cubed. Well, to take the derivative, we can just find the derivative of the first piece, the derivative of the first piece would be 2x, thank you power rule, 2 jumps in front, subtract 1, and now we can subtract this piece. So derivative of this, power rule, it goes in front, 3x squared. So if they're adding, you can add the derivatives. If it's subtracting in the function, you can subtract the derivatives. It's very handy, it's going to speed things up. And again, I'm not going through the derivation and making you prove that these formulas are true. I'm just saying, here are formulas, here's how to use them. So we had the constant rule, and then there's also what they call the coefficient rule. It's basically saying you can factor out a constant. Coefficient rule. So the rule looks like this. If you have f of x is equal to some constant times a function, then the derivative, f prime of x, is equal to the constant times the derivative. We can factor a constant out in front. For example, suppose you have f of x is equal to 2 times x cubed. So the derivative, f prime of x, I say prime, that means derivative, equals 2, just take the 2 out in front, and now take the derivative of this guy. Power rule. Who's your friend? It's the power rule, 3x squared. So the answer here would be 6x squared. So we can find the derivative of a constant is 0. The sum, you can add derivatives. Difference, you can subtract derivatives. Coefficient, you can pull this constant out in front. So I'm going to show you some problems where we put all of these rules together and start working these derivatives much faster than if you had to use the limit definition every time. For example, question 5, it just has this function y equals 6 minus 8x plus 2x squared. And it says find the derivative. So you could think of this as dy dx or y prime if you like. So the derivative of 6 is 0, constant rule, minus 8, the constant factors in front. The derivative of x is, you can think of this as 1, that's x to the 1, x, subtract 1 to the 0, plus, I'm doing this like with a step you guys probably won't include, 2 times the 2 factors out in front, power rule, this 2 jumps in front, subtract 1, 2, to the 1. So this whole thing equals negative 8, because x to the 0 is 1, plus 4x. That's the answer. And for something like this, you guys are probably going to get pretty fast, and you're going to look at this one and go, minus 8 plus 4x. Check. Let's try another one. Here's question number 11. We have, I'll write in yellow so you can see it better. W equals z to the 7th minus 3z to the 6th plus 13. So the derivative of this, you could think of that either as dy, the derivative of y in terms of z, or, because we have y's and z's, or y prime, or w prime. I said y before, that's a w. So same thing, even though it's a z, it doesn't matter. Power rule, 7 jumps in front, 7z, subtract 1 to the 6th, minus 3 times, 6 jumps in front of the bus. It's sacrificing itself for the power rule. Subtract 1, 5, plus the derivative of 13, that's a constant, is 0. So the answer is 7z to the 6th minus 18z to the 5. I crossed my z's so they don't look like 2's. Okay. So another type of problem, once you're kind of starting to get comfortable with these derivative formulas, is we have these problems where you're supposed to then do a little bit more of an application with remembering that the derivative is the slope of the tangent line at a point. So here's an example, question 27. It says, write the equation of the tangent line to the curve at the indicated point. So our goal is to write the equation of the tangent line. So the equation of a line of the tangent line at a point. So we have a curve. We're going to write the equation of the tangent line at the curve. So for 27, we have y equals x cubed minus 5x squared plus 7. And we're saying at the tangent line, so it's something that looks like this, woo, at the point x equals 1. So some point here, x equals 1. there's a line that is tangent. I picked that point. I don't think x equals 1 is up there, by the way, but I wanted to make it a point where I could draw a line that would be tangent. So we're saying, what is the equation of that line? And remember, lines have the equation y equals mx plus b, something like that. So that's our goal. So the slope of the tangent line, the slope of the line that is tangent to the curve at the point, slope of the tangent line, is given by the first derivative. So that's why it's in this derivative section. So we'll take y prime, the first derivative is 3x, 3 jumps in front, subtract 1 squared, minus 5 times 2, 2 jumps in front, x, subtract 1 to the 1, plus 7, derivative of constant, 0. So this is 3x squared minus 10x. So this right here, the first derivative, this is an equation that gives us the slope of the tangent line at any point. So it's not the equation of the line at this point, it's the equation that will give you the slope. It's a bit tricky. So at the point x equals 1, what is the slope of this line? The slope is equal to, let's plug it in, y prime, evaluated at 1, so when x equals 1, 3 times 1 squared. Oh, I can do this one without my calculator, right? That's 3 minus 10, do you see? Do you follow along? Equals negative 7. So I'm saying the slope of this line equals negative 7, but I'm not done yet because I need to find the equation of the line, not just the slope. So to do this, we're going to use the point slope form. And in order to use the point slope form to find the equation of a line, you need a point. We've got the slope. Here's the slope. It's the slope if you're using this mx plus b thing. So we need a point. And we have to use the point x equals 1 because that's the point we're interested in. So when x equals 1, what is y? Well, we're going to use this formula here to find that point. So when x equals 1, that implies that y on the function itself, the little curvy function, y equals 1 cubed minus 5 times 1 squared plus 7. Okay, this is 1 minus 5 plus 7. 8 minus 5 is 3. So now we have a slope of 7 and a point. We found a point on the line that is 1, 3. I'm going to get a new piece of paper here. File new. We need more space. Take a breather. Get some space. So here's what we're saying. Here's our slope of our tangent line is equal to negative 7. Oops. Negative 7. And a point on the line. The point is equal to 1 and 3. So now if we want to find the equation of the tangent line at the point, we're going to use this formula. Remember, y minus y1, algebra, raising its ugly head, equals m times x minus x1. So we plug in y minus 3 equals the slope, negative 7, x minus 1. So we have y equals negative 7 x from here plus 7 minus 1 plus 7 plus 3. Where'd the plus 3 come from? Over here. I added 3 to both sides. So this equals y equals negative 7 x plus 10. So this is the equation of the line tangent to the curve at the point x equals 1. Equation of tangent line. You like that? Tangent line. So again, we had this function that looked like this, whoop, like that, and it was y equals x cubed minus 5x squared plus 7. And I'm saying at some point x equals 1, right? I'm going to pick this point. There is a line that is tangent, not the one I drew, but that line is tangent to the curve at that point. And that's telling us sort of where the curve is going and the instantaneous rate of change at that point. And the equation of that line is y equals negative 7x plus 10. And then your book also says for these problems, as a check, graph both the function and the tangent line. Let's see if I did that. Hold on. X cubed minus 5x plus 7. Look, it's just what I said it would be. And x equals 1. I wasn't too far off. Oops, there's that point. And now we went to all that trouble to find the equation of the tangent line, negative 7x plus 10, and it'll graph it for us. You'll notice it is so tangent that it almost looks like the same point. But right there, that's the tangent point, 1, 3. So that point is both on the line and on the function. And if we zoom in, again, this tangent line and this function, the way this graph is, it looks like they just mold. It doesn't look tangent at all. It looks like they traveled the exact same path for a long time, but actually they're only touching. Barely, just a little kiss of a touch right there at 1, 3. So that is how you do these problems. So hopefully these derivative formulas will allow you to find the derivatives much quicker, and then you're going to start remembering that the derivative is the slope of the tangent line and it's the instantaneous rate of change. And then there's also some applications where the slope is the marginal rate of change, and we'll get into more of those as you do more derivatives.